Hello and welcome. My name is Alfredo Goddi. I am a radiologist with more than 3 decades of experience in ultrasound. I am the director of the SME Medical Center in Varese, Italy. Among the years, I focus my research on physical principles of ultrasound, varying from color Doppler and elastography. In the last few years, I concentrate my attention on and academic papers on the clinical application of vector flow to the carotid bifurcation. In this presentation, I would like to show to you the new opportunity in diagnostic vascular imaging offered by the vector flow technique. Today's topics will consider basic principles and clinical applications of vector flow, hemodynamic evaluation of the carotid bifurcation with high frame rate vector flow, and lastly, the evaluation of shear stress in the arterial wall with vector flow. Vector flow is a Doppler technique which provides an angle-independent information on magnitude and direction of velocity vectors. This technique, named V-flow, available on the Resona 7 Mindray system, represents an implementation of the vector projectile imaging method. It provides a very high frame rate flow imaging through multidirectional transmission and reception of plane waves at a PRF between 3 and 10 kHz, achieving about 400 or more than 1000 frames per second, while interleaving high-resolution B-mode imaging. What is high frame rate vector flow capable of? Vector flow shows all velocity vectors in a selected region of interest and highlights streamline and vorticity distribution, allowing a spatial resolution of 0.2 mm. As you can see in the picture on the right, it uses arrows to indicate the flow direction. In addition, the length and color provide information on the velocity magnitude. Different color maps are available. The most frequently used codes the different velocities as indicated in the slide. In any case, keep in mind that the longer the arrows, the faster the flow. How does it work? V-flow is usually applied to interrogate the flow for 1.5 seconds in order to study at least one cardiac cycle, and generates a video clip of several images which can be visualized frame by frame for further analysis. Let's move from the basic principles to the clinical applications. These are the 4 main clinical advantages provided by high frame rate vector flow. Now we'll focus on the first one. The first key point is V-flow allows the dynamic display of velocity vectors. To demonstrate this in sentence, we'll compare color Doppler and V-flow. On the left side, we see what color Doppler shows on the screen after the 1.5 seconds flow interrogation. On the right, you see what really happens in those 1.5 seconds as shown by V-flow. We are able to identify flow streamlines, layers separation at the level of a flow divider, layers detachment from the wall with vortices and counter eddies in the carotid sinus. The second one, V-flow visualizes even transient events. Thanks to V-flow's high frame rate, we can easily detect all the stages of the cardiac cycle, which wouldn't be able to see as clearly with conventional color Doppler. Before talking about the third key point, a few considerations are necessary. Conventional ultrasound doesn't allow the quantification of complex flow. our current knowledge is more theoretical and still lacks sufficient practical support. And high frame rate vector flow is more efficient in providing qualitative and quantitative information. We can now consider what happens to laminar flow at the level of the carotid bifurcation, where the sinus enlargement promotes the flow layers separation. As the red arrow indicates, the high velocity layers move near the flow divider. On the outer side of the vessel, inside a separation zone, highlighted by the blue arrow, a secondary flow develops. Color Doppler highlights the separation zone in a basic blue color. The flow, on the other hand, is able to depict the actual movement of the flow layers. As demonstrated in a recent paper of ours, the flow highlighted a larger extension of the complex flow compared to color Doppler, and vector depicted different complex flow patterns. A strong correlation was found between the ICA to CCA diameter ratio and the complex flow extension. Moreover, as you can see in the slide, the flow outlines the streamline's behavior in different anatomical conditions and permits the analysis of complex flow, allowing to distinguish different flow patterns such as recirculation, counter-eddy, vortex, and helical trajectory. Let's consider now the role of the flow in presence of a low-degree stenosis, in which the increase of velocity is not relevant and the role of a conventional ultrasound Doppler technique is less evident. Generally speaking, V-flow allows better understanding of the streamline's progression and vorticity formation and depicts the hemodynamic influence of some plaques which would otherwise be considered not significant. In this case, V-flow shows laminar flow before the plaque, eccentric maximum velocity vectors, and a large complex flow along the opposite wall, where oscillating flow, indicated by the yellow arrows, is evident. Again, in case of critical stenosis, the flow gives a more precise depiction of the flow behavior, highlighting its random movements. Even in presence of severe stenosis, the amount of turbulence is better highlighted by the flow than by color Doppler. However, as hemodynamics become extremely complicated in some conditions, quantitative measurements are necessary. Let's move to the last key point. The flow allows flow quantification through a special feature which automatically calculates the maximum velocity vector inside a region of interest defined by the operator. It permits a more precise grading of stenosis, as you can see in this slide, which compare conventional Doppler with high frame rate vector flow. To complete the last key point, we will consider the wall shear stress measurement. In this recently published paper, high frame rate vector flow has been proposed to measure wall shear stress. Of the mechanical forces acting on the vessel wall, we will examine shear stress, which is the tangential force exerted in the direction of the blood flow. This force plays a key role in vascular reactivity and atherosclerosis development. As you can see from these pictures, The shape, the orientation, and the turnover of endothelial cells changes depending on the flow behavior. There are two existing types of wall shear stress. The unsteady one, promoting endothelial dysfunction and the expression of adhesion molecules and genes, and the steady one, which has a beneficial effect on the endothelial cells. The reference values for wall shear stress have been already established in the literature. For example, the normal maximum wall shear stress in arteries is between 1 and 7 Pascal. Regions prone to plaque development experience a mean wall shear stress between minus 0.4 and plus 0.4 Pascal. These low values are usually found on the opposite sides to the flow divider in the carotid bifurcation. V-flow supports a series of 6 wall shear stress measurements along the vessel walls. We can find maximum and mean wall shear stress values in a cardiac cycle. We'll take into consideration 3 clinical examples of wall shear stress findings in different flow conditions. In the first case, V-flow shows uniform laminar flow and the wall shear stress mean values appear to be normal. In this second case, at the level of a reverse flow area in carotid sinus, the values of mean wall shear stress are extremely low. This last case of complex flow shows abnormal mean wall shear stress values on the opposite side to the flow divider. Before concluding, I would like to show a clinical case of severe stenosis of the carotid bifurcation, well defined at B mode and Doppler ultrasound. In this clinical case, the maximum wall shear stress values at the level of the stenosis are inside the range of variability, around 5-7 Pascal, as highlighted by the green arrows. Nonetheless, abnormal values of low mean shear stress were detected at the edge of the plaque, as highlighted by the yellow arrows. The velocity oscillations are depicted by the velocity curves indicated by the red arrows. These findings have been confirmed by computational fluid dynamics studies. Here you can appreciate the dynamic vector velocity map generated from the CFD, which highlighted the oscillatory low flow at the edge of the plaque. High frame rate V-flow obviously has some limitations which can affect wall shear stress measurements. Specifically, wall shear stress can currently be estimated in a 2D imaging plane only. Nonetheless, areas of oscillating wall shear stress can be easily detected with high frame rate vector flow on the basis of the flow behavior. Preliminary research findings are encouraging and show that high frame rate wall shear stress values seem to be comparable with the CMF wall shear stress ones. And if the preliminary findings will be confirmed, high frame rate vector flow could identify patients at a high risk of plaque development or plaque rupture. Based on what we have seen, let me come to some conclusions. The flow shows detailed spatiotemporal characteristics of the flow in the carotid bifurcation and demonstrates the strong effect of vessel geometry on the flow patterns. It provides various quantitative results useful for hemodynamic studies and could define the impact on the hemodynamics of the vessel stenosis. And last, the flow allows to identify patients at high risk of plaque development. Thank you for your attention.